the recording. Let's go full screen. So this time I did prepare the lecture slides. I had time to do that. So 10 questions, they are not enumerated, so you won't see the numbers 1, 2, 3, 4, right? But I know that there are 10 of them. So this is the question about the relation. 3 different types here, the relations we are given. One, as a pair. Second, as a formula. And third, as a graph, right? So here, what we have in the first place is that we have a correspondence between the values from the domain and the values from the range, right? So all the first components, right, of the tuples are representing the domain, or the second ones are representing the range. Now, if I look at it, what I should not see is that the element from the first place, the first component, corresponds to more than one different value of the second component. If I see that, then it means that it's not a function, right? So this is what I'm talking about. Where is my stylus? So graphically, sometimes it's much easier to understand. So for example, these are my values from the domain, right? Like I have maybe 1, 2, 3, 4. Now they do correspond to something, right? Now, for example, 1 corresponds to 10, and maybe 2 corresponds to 27, and maybe 3 corresponds to 45, but then 4 corresponds to 10, right? That could happen. That is fine. Now, what I don't want to see is that 1 corresponds to 10 and it also corresponds to 27. So when we have these 2 connections of the first component value to the 2 different or 3 different, more than 1, second component values, it means that it is not a function. Now look at these tuples. See if you can find anything bad in terms of that it's not a function. Okay. See if you can find something like that. See if you can find something like that. No, I can tell you for sure, I am seeing a problem. This will not be a function. What is it, right? What is the problem?
The problem is that 1 corresponds to 7 and to 4.
Exactly. I absolutely agree with you. Yeah. So this 1 corresponds to 7, and this one is also corresponding to 4. That's bad. So because of this, it is not a function, right? So not a function. Exactly. Okay. Excellent. Now, take a look at the second one. Now, in the second one, we have a relation. And if we have it in a complicated form, not like y equals to something, right away in terms of x, we need to solve it for y, right? So what we need to do first is we need to solve it for y. Try to do it. I'll give you like a couple of minutes. Try to solve it, and then we will talk about it, whether it is a function or not, right? Try to do it on the side. I'll give you 2 minutes, and then I'll put my answer so you can compare yours and mine, and then we'll discuss whether it is a function or not. And I'll silence my phone meanwhile. Minutes, and also I'll keep an eye on the timing. In 16, okay. 1 minute. Okay, so this is what I did. I sent, let me check the answers. Maybe somebody sent me something interesting. Okay, it's not a function, Jelly. Yeah, I absolutely agree with you. It is not, oh, wait. No, it is a function. Yes, I was so devoted to saying that it's not a function that I said it's not a function. It is a function. You'll see it. So here is the trick. We are moving this y cube to the other side. I could do it otherwise. It's not a big dish. It's not a big difference. I could keep it and I could move x to the other side. It just, for me, why it is so buying is that I will get rid of this minus sign, okay? So I sent it to the other side. I got y cube here, and then I sent 10 to the other side. So this is what I got. Y cube is equal to x cube minus 10, right? And then I need to extract the cube root from both sides, right? So I will say y is equal to cube root of x cube minus 10. Now, do you see that I'm not putting the plus minus here? That might, that could be the reason of why you thought that it's not a function, right? So I'm not going to put plus minus here because cube has no issues with negative number, right? So for example, if I'm saying 2 cube, it is 8. And if I'm saying negative 2 cube, it is negative 8, right? So when I'm extracting a cube root, I don't need to take care of the minus and plus like we did for the square. Because when we have a square, for example, when x squared is equal to 4, this is the case when I have two possible values. X is equal to negative 2 and x is equal to 2, right? That's why we put the plus minus when we extract a square root. It would be true for all even power. But for all odd power, they do preserve the sign. So I will not put plus minus here. Now, why is it so important to me? Because it will exactly show this case when one value of x corresponds to two different values of y, right? So that plus minus exactly the reason why we have issues sometimes. And since I don't have it, no matter which value of x I use, it will be always be producing one value for y, right? Like there is only y to interpret this, one way to interpret this expression. If x is 1, 1 minus 10, it's negative 9, cube root of negative 9, whatever it is, I cannot extract it, right? And so forth. So it is a function, represents a function, right? Okay, so for this one, yes. Now for the next one, do you remember what test would I be using? Do you remember which test to check whether it's a function or not? What was the test? I'll give you a hint. Vertical line or horizontal line test, right? Vertical line or the horizontal line test. Try to recall, what was it? It was a vertical line test. So what we do is the vertical line test allows us to see the number of intersections with the graph, right? And if we have more than one intersection like we have over here, then it's not a function, right? So over here, we will have even 1, 2, 3, 4, right? So we'll have even 4. So as soon as any one of those vertical lines intersects the graph in more than one places, it's not a function. And here is the rationale for it. Why is it the vertical line test? So you see this value x over here, right? So it has two values of y that correspond to it. This one and this one, right? Wait, sorry, this one, right? Oh, this one, right? So two values of y. So it violates the definition of the function, right? So that's why it is a vertical line test. Because when we draw the vertical line, for this particular value of x, we have the correspondence with the y's, right? And if we have more than one, then it means that it is not a function. So it was the vertical line test. And do you remember what do we use the horizontal line test for? To check if the function is invertible, right? Just if it has an inverse. So that we use it for that one. So we'll just, we'll talk about it later. But so two tests, two nice tests. And once again, it's good to remember them, right? Because it can really help us. Okay, so let's go to the next question. Here, I'll give you 5 minutes to work on it because I want you to make answer, to answer all of these questions. And there are a lot of them, right? So I'd like you to answer all these questions. And then, I know that it's a lot to put into the chat message. So how about this? Into the chat message, just put an answer to the last 4 questions. Okay, last 4 questions, but work on all of them. Okay, so it will be also the flag for me that you completed it. Okay, so do all of the items, but put the answers into the chat messages only for the last 4 items. Okay, so I'll give you 5 minutes to work on that, and I'll pause the recording for the time being. Okay, resume recording. Okay, so on the left, everything is defined, right? No matter what X value I have. But over here, I might be a little bit hesitant. So here is the trick. At 1, the value of the function is 0, right? Because it's this point. But at 0.9, it's somewhere over here, right? So what was happening with the function is at 0, it began to increase, right? It was growing up to this 1. But this 1 is excluded, right? So at x equals to 1, the value of the function f, or whatever it is not 1, it's a 0, right? So it was defined everywhere here. It's not defined here for this part of the graph, but it is defined as 0 at this x. And then we continue. So at 2, the function is defined. At 4, the function is defined. At 6, the function is defined. But here, I think I will have to stop, right? Because I have a point here as an endpoint, which shows that the graph does not continue. So I need to figure out what is this mark for, right? Now check this one out. I'll use the black color. So this one is 5, right? So it means that 2 of the squares is a 1 step. So 1 of the squares should be 6 point, what is it? Half, right? 6.5. So this is where the domain ends. And therefore, the domain for us will be from negative infinity. You remember we always excluded, right? Until 6.5, including, right? Including. Excellent. Now, let's talk about the range. Now, same situation here. The range is all the one values, right? All the values that the function can get. And what we have over here is, it can get the value of 4, it can get the value of 2, it can get the value of 0. So it can get these values, right? Between the 0 and 4, like these ones, definitely there. Now, what happens below 0? We go to infinity. So for the range, right, it will be heading to the negative infinity. And above 4, we will never rise, right? We will never rise because we don't have the graph there. So the 4 will be the ending point for the range. Now, don't worry about this part, because this part is not essential to us already here, right? All those values we can get. So this one, I'm not even interested because I don't have a continuation here. Let me see the check. Would you be able to do the number line for this function? Number line, same thing. So if you will be projecting all the points on the number line, right? Just imagine projecting all of them. They will be all cluttered here. And then this one will be also cluttered. Yeah, so you could do the number line projection as well here, if I understood your answer correctly, Alex. Right. Okay, so here is our range from negative infinity to positive 4, including. Okay, now on which interval the function is increasing? Wow, here it is increasing, right? So here it is going up, it is increasing. Here it's decreasing. Here, again, it's increasing. And here it is increasing, right? Now, remember how we did the intervals for increase, decrease? They never included the bounds, right? So don't forget it. And the intervals of increase and decrease is about the x, right? So on this interval, like, up to here, the function is increasing. On this interval, up to this one and up to this one, so we could say that it's up to this one, right? So we can include the entire interval because here the function is indeed increasing, right? So, you know what? No, I would be more precise. I would exclude this point, right? I would exclude this point just to kind of be on the safe side. And I'll tell you why. Because here the behavior of the function is discontinuous. So it's not like it's continuing its behavior, right? It's not like that. So that's why in order to be more formal, we have to exclude this and this. This will be more appropriate and more correct. So the intervals of increase, decrease from negative infinity to, what is it, -2? From 0 to 1, and from 1 to 6.5, 6.5 here, right? From 1 to 6.5. This is a point, right? Decimal point. So something like that. This will be our intervals of increase, right? Let me know if you have any questions. Okay, so what I will do is I will erase some of the picture drawings because, I need to see the graph. My eraser is glitching. It's drawing, it's weird. It's okay. Now, the next question is if the function is even, odd, or neither. Do you remember that the even functions are very easy to see? Like, for example, if this, come on, if this function would have the graph like this, so it would go over here, and then it would go here, like this. This is an even function, right? This is even function because even functions are symmetric about the y-axis, right? So this would be the even function. So obviously it is not. Now about the odd function, you remember how they're symmetric about the origin? So for example, if I grab this point over here, right? And the point has coordinates -2, 4, right? And if I not flip them, right? Not flip them, but change the signs of both, right? So I'll change the signs to +2, -4. So this point should be also on the graph. So it's 2 and it's -4, it's somewhere here. Obviously it is not, right? So when I do this and when I see it, I'm saying, no, it's not an odd function. Now, can you recall when do we switch the coordinates? For which case? For which case when we are checking what about the graphs? I'm giving you some time to kind of, try to recall it, right? So what I did here is I negated both of the coordinates, right? But when do I switch them? What am I checking with the switching of the coordinates?
The inverse?
Inverse, exactly, excellent. The inverse function, yes. So if I have two graphs of the function and of the supposedly inverse of it, that's how I check. I flip the coordinates, exactly, yes. Wonderful, okay. So it's not even, it's not odd, so therefore it is neither, right? Okay, excellent. Now for the inverse function, we will do the horizontal line. So I'll do this line and I'll see these two intersections and I'll say it does not have an inverse, right? So the horizontal line test is the following. If you find one horizontal line that intersects the graph in more than one spot, right, more than one point, then it does not have an inverse, right? So if I draw it here, there are no intersections, so it's kind of everything is okay. If I draw the horizontal line here, everything is okay. I have only one point intersection, but that's not what I'm looking for. I'm trying to fail the test, right? So that's why I will be looking for the places where I have many, like, at least two intersections, and then say, No, it does not. Right? No, it does not. Excellent. Now,
I'm sorry to interrupt, Professor. I just have a question about the previous question.
yeah, go ahead.
You said even functions are symmetric and odd functions have an inverse?
No, even functions are symmetric about the y-axis. Now, the odd functions, they are symmetric about the origin. But with the graphs, it's usually, kind of hard to flip them and rotate them. What's easy to do is to change the coordinates signs. That's easier. So we are not switching them. We are we're negating both coordinates. We negate the x coordinate, we negate the y coordinate, and this point that we got over here should be also on the graph. Then it means that, it is an odd function, and it should be working for any point you grab.
Okay, thank you.
Okay, let me remove the last drawings, over here. Now, for these evaluations, be very careful. It's always tricky with the signs. And it's also tricky with these places. So check this out. F of 1 is equal to 0. It's not equal to this one because it's excluded point, right? It's this one, it's a 0. Now, f of negative 4, we go over here, we grab this value, it's a 4, right? So I'm putting 4 here. So it is 0 plus 4. So I'm getting a 4, right? Okay, now while I'm doing this, I want to erase some things like this so that, it will be like cleaner. Okay, now the next question is the absolute maximum. So absolute maximum, it could be more than one, by the way, right? Well, okay, it will be one value, but it could be reached at many places, right? But it's always one value. It's the highest possible value of the function. And of course, we cannot have it as the infinity, right? So we cannot. No, it should be something that we can reach. Now, in this case, if you look at the graph of this function, right? Let me use the mouse over here. This is the tallest point on the graph. That's the absolute maximum, right? That's the absolute maximum. Now, you have to be very careful with the definition. So let me put that the absolute maximum is 4. It's a 4, right? So it's this value over here. Now, the absolute maximum value is the y coordinate. You could say that it happens at -2, but this is what we are interested in, right? Yeah, we could be asked like, where does it happen, right? Where does the function have the value of the absolute, right? But but usually we're interested in the y value. What's the highest value the function can get, right? Now, look over the definitions very carefully, because if I wouldn't have this part over here, right? This part, because this one is also a relative maximum, right? It's also a relative maximum. So if I wouldn't have this part over here, it would be my absolute maximum, but it will not be relative maximum, okay? Because I cannot find an open interval around it where it's the highest value, okay? So I don't have this left part, it's undefined here. So it will not be a relative maximum, okay? So it's really extremely important to look into the definitions carefully. Go over them, make sure that you review them, okay? Now, in terms of the relative or local minimum, so what, two ways to say it, relative minimum or local minimum. On the final exam, be ready to see only one term. So either relative minimum or local minimum. So what it means is that it happens somewhere on the graph of the function that it's reaching like a smallest value locally, right? So for example, if you look at this bump, it's usually the bumps, right? So if you look at this bump locally, like for example, on this open interval, this value is the smallest value for the function, right? But it must be happening on an open interval, right? So, and no matter what value I grab there, it will be more than the 0, right? Because it's a 0. Once again, it's also in terms of the y coordinates, right? So it's a 0 there. And once again, locally, there is no value that is below it. Now this one I cannot choose because locally, once again, right? Like if I choose it here, locally here, I will have values smaller than that, right? So when I have an arrow, it means that I cannot do a local maximum, minimum there, no maximum, right? So I cannot have it there. Okay. Now, about this point, it's not an absolute maximum because it's lower than the 4. What is it? Like, 1.8? I don't know. No, it's 0.8, right? 0.8, something like that. So it's too small. And it's not a local maximum either, right? So for the local maximum, I should have a hump. This would be local maximum, right? This is local minimum, local maximum, local minimum, and so forth, right? But not at the end points. Okay. Let me know if you have any questions. Everybody's good? Okay, so let's go to the next one then. Okay, so here is the graph transformations, right? We are not given the function itself, we are only given its graph. And what we are asked to do here is based on this graph, this is the graph of the function g of x, we need to graph negative g of 2x minus 3. Now, what we usually start with is what's the vertical change, what's the horizontal change, right? So what I will do is I'll begin it and then I'll ask you to graph it, okay? So check this one out. Whenever the input is modified, that's a horizontal change, horizontal. Now, what do we have here? We will be multiplying every value of x by 1 over 2. You remember this, right? So x value by 1 over 2, right? 1 over the coefficient. So it means compression. Compression or shrinking. So once again, in Zai book, it was compression. But in the Pearson book, it was shrinking, if my memory doesn't fail me. Shrinking. Okay. So that's the horizontal change. And usually we prefer to do them first. Now over here, this is a reflection, but it's a vertical reflection. It's a vertical reflection about the x-axis. And I'll tell you how I know. For example, just imagine we got the 3 here, right? So 3 is this one. And then you multiply it by -1. So it goes down. It's reflected about the x-axis, right? So this one is vertical reflection about x-axis, right? Because every y value will be multiplied by -1. Now this one I will do at the end because it's a vertical shift. So we see, it's easier, I don't know, it's easier to me to do the vertical reflection first and then the shift, right? So now the last one, this one, it's a vertical change. Now what do? Whatever value we get here, we will subtract 3 from it. So it means that we bring it down, right? So it's a vertical shift, 3 units down. Okay. Now I laid out everything for you. What I'm asking you to do in return is to graph it. So please grab a piece of paper, do the original graph, and then try to do all of these transformations to see what are you getting at the end. Now you could probably guess that you see I finished this line, I added it, right? I only had the picture of this. So I added this line. So we will have to go down. It's because of the shift 3 units down, right? So you will see that we will have to do that. Okay, so take your time. I'll give you, what is it, 11? Let me see, 59, 50. I'll give you 5 minutes for that, okay, to make sure that you will do it correctly. Well, correctly, incorrectly, doesn't matter as long as you do it. Because if you didn't do it correctly, then we will fix it, right? but please work on it. Recording. Okay, I have my note in front of me. So let me do these transformations for us now, and I will use the same color as I marked the transformation with, right? So where is my pen? Here. The first thing I would do is the horizontal compression, right? So what happens then? This point, let me draw it. This point has an x value of 2. Now the 2 will be multiplied, let me do it here. 2 will be multiplied by 1 over 2. So it will become 1. So this point x coordinate is now moved over here. It's over here, right? Now, this point has an x value of 0. If I multiply 0 by half, it will still give me 0, right? So this one stays in place. Now, this point has the x coordinate of negative 1. If I multiply negative 1 times 1 over 2, I'll get negative half, right? So from here, it moves over here, right? Okay, now this point has the x coordinate of negative 2. If I multiply it by half, I'll get negative 1, right? So it travels over here. And finally, this point, it has the x coordinate of negative 3. If I multiply negative 3 by half, I will get negative 3 over 2, which is negative 1.5, right? So I'm moving it over here. So this is how the graph looks now. I'll draw it from here. Oh, 1.5. Sorry, let me do this. I moved it to the 2, negative 1.5. Okay, here, and then up here, and then here. So it was compressed, right? It shrunk. Now, let's do the vertical flipping. So it's called that sometimes vertical flip, right? Vertical reflection. Now, what happens with the y coordinates? I'll start with this point. This point has a y value of 1. Well, it gets a negative in front of it, so it becomes negative 1. So it was rotated, right, or reflected above the x-axis. Now, this point has the y value of 0. It will stay in place because 0 multiplied by negative 1 is a 0. But this one will be flipped over here, right? So instead of the negative 1, I'm getting 1, right? So this is how it went, right? So this point went over here, and then the rest of them did the same thing. Okay, now what happens with this point? This value is 3. If I multiply it by the negative 1, I'll get the negative 3. So here it is, negative 3, here, right? So I could draw the line like this, right? And let me erase the point from here, not this one. Point from here, yes. Okay, let me do this because I don't want to have the pink one here, like this. This is better. Okay. Now, what happens to this point? It has a value of 2, but it will become negative 2 when I multiply it by negative 1, right? So it goes over here. So this is how the graph is reflected about the x-axis, right? So just imagine it flipping it over the x, right? Okay, and then finally we'll have vertical shift 3 units down, right? So for that, I need to add up more units. 1, 2, 3. So it will be like negative 6 over here, right? So let's start with this point. We go 1, 2, 3 down. Let me change the color. It will be the orange one. So over here, right? Now let's move this one. 1, 2, 3 over here. So this is our line, right? Now let's move this one. 1, 2, 3 over here. So let me draw it like this. Okay, now let's move this one. 1, 2, 3. This. Okay. And then this one. 1, 2, 3. Here. So here is the graph then. This is our final graph. So the graph in orange is the answer. Okay. Let me know if you have any questions. Everybody's good? Okay, let's proceed then. Okay, so I'll remove the bar for the time being. So here we have two functions, and we are asked to find the F composition G, right? And then F combination G, right? Combination. So it's just times, right? F times G of X and F composition G of X. Now for each of them, we'll be asked to find the domain as well here, right? Try to recall what's the difference between the composition and the combination, right? When we multiply F by G and when we compose the two functions, right? Now, while you're thinking about it, I'll grab my annotation tool. I think I will need it anyway. Okay, so the composition means that we apply one function and then the other. Now the function to the right is the rightmost function is applied first. So we will have it as F of G of X, right? It just follows the order of the writing, right? F of G of X. Now, when we have the combination of function, it means that we just multiply them. F of X times G of X, right? So I'll just use the expressions to substitute them over here. This one is, easy. Now here, I first need to apply G of X, meaning plug in 1 over X. And then to this expression, I will have to apply the expression for the function of F. Now, let me give you 5 minutes to work on all of these items. If you can, please, let me see how big of the expressions are not that, weird. You will have to put the SQRT there, but, you can do that. So if you can, please, put me the expressions for the composition of functions and combination of functions into the chat messages, and then we can discuss the domain later on. But if you have time, please also think about the domain. Try to recall, how do we find it? Okay. So 5 minutes for us to work on this problem. One by one. So here is my pen. First thing I will do is I will plug in this expression for G of X in the composition of the functions. So I'm doing F of 1 over X, right? Now, what I'm going to do is to use this expression instead of this X in the formula for the F of X, okay? Let me do it. So I am getting square root of 1 over X minus 2. We can continue working on it. For example, we could rewrite it with the denominator X and say here 1 minus 2X. That's not a big deal, but we could stop here. So it doesn't matter that much, right? This one is good enough. Now, about the domain. Do you remember that we have 2 stages there? First, the function G was applied. So we need to look into the G's domain. So this work, this item, I will be doing here. So the first thing I want to do is the domain of G. Domain of G. Remember how we used to denotate it? D with the subscript G, right? Okay, so what is it? This is the expression I'm looking at, right? Now, this function is defined everywhere except when X is 0, right? So X equals to 0, exclude from the domain, right? Now, what it means then is our domain here will be from negative infinity to 0 and from 0 to positive infinity. But this is only one step. This is the first step. The next step will be to see when the values of 1 over X, so when all of these values satisfy to the domain of F. Now, it might sound, very hard to do, but we can look at this expression, not at the simplified one, but at this one. What we want to have from here is that number 2, that the 1 over X minus 2 should be greater than or equal to 0. Isn't it so, right? Because it's a radical. So the radical is undefined when the expression inside is negative, right? And it is defined when it's 0, and it is defined when it's greater than 0. So this is what we will be working on. Okay, we will have to solve it, right? So I'm moving to the other side. 1 over x greater than or equal to 2, right? Okay, now what we can think of, because right now my next step will be to multiply both sides by x. But before I do it, look at this expression. If x is negative, right? If x is negative, we are in trouble, aren't we? Because this entire expression will be negative. So the first thing before I proceed working here, because what I'm planning to do is I'm planning to multiply this side by x and this side by x. But you remember how it is with the inequalities. If the number I'm multiplying is negative, then I need to switch the direction, right? So I have no idea what the x is for now, right? So I need to establish where the x will be positive or not. That's why I'm looking back at this expression over here, right? And I realize that if the x is negative here, then both of these numbers will be negative, and I will be getting a negative number in the radical. So I can say that x is greater than or equal to 0, right? So this is another limitation that we have, right? First, we excluded the 0. Secondly, we said that it should be greater than or equal to 0. We'll have to combine all of them at the end, right? And then now this, at least now I can do this multiplication, right? So when I do the multiplication, this x cancels with this x, right? And I am getting 1, apologies. Okay, I'm getting 1 is greater than or equal than 2x. And now I can finish it by dividing, let me take another color, dividing both sides by 2, right? So I am getting that 1 over 2 is greater than or equal than x, or in other words, x is less than or equal to 1 over 2. So this is my third limitation that I will have to use, right? So first limitation, that x equals to 0 is excluded. Second, x should be greater than or equal to 0. We'll exclude the 0 here. And last one, that x should be less than or equal to 1 over 2. I have to combine all of them to produce the domain for this function. Now let's take a look at it. X 0 is excluded. So from here, I'll cross out this equality, right? So it's only greater than 0. And then it's less than 1 over 2. We have our domain. So it will be from 0 up to 1 over 2, including, right? That will be the domain. Let me mark it, that it's the answer, right? That will be the domain. Let me know if you have any questions about the work. Right? I need to erase this. Like extra lines here, I see. This is when I sometimes touch my touchpad and it draws things. Okay, everybody seems to be doing good. Okay, so let's do this one. Let's work on it, but I'll choose another color so that they will not be mixing up. Now, the expression for f of x is this entire radical, right? So I will put square root of x minus 2 times. And then I would grab the expression of g, so times 1 over x. The only thing that I will do here is just place the square root of x minus 2 into the numerator, right? That will be my answer for the combination of function, right? Okay, now we need to look at its domain. And do you remember what we used to say for, it was for the 3 cases when we have f plus g, f minus g, or f times g. We grab the domain of f and we intersect it with the domain of g, right? So the domain should satisfy to both of the functions, okay? Now we already know what's the domain of g, right? The domain of g is that we exclude the 0, right? So let me put it up. Put it up. So the domain of g is from negative infinity to 0 and from 0 to positive infinity. The domain of f, right, would be that x minus 2 should be greater than 0. X minus 2 should be greater than 0. should be greater than 0. So in other words, oh, greater or equal, right? Greater or equal. So in other words, it means that x is greater than or equal to 2. So its domain will be from 2 to infinity, right? And we need to intersect these two intervals. You can even draw them, right? So for example, this is 0, this is 2, right? So this domain will be, let me do it in the color orange, right? So it will be, including, apologies. I forgot to include, right? I should include it, okay. So it will be from here and onward, right? And then, let me choose the color. I'll do this one in purple, right? So now this one is from negative infinity up to 0 and from 0 to positive infinity, right? So it's this one. So you could see that the intersection happens only here, right? So therefore, the domain for the combination of the functions will be from 2 to positive infinity. So let me put it up. Domain of fg, right, is from 2 to positive infinity. So that's our last answer, right, for the last item. Okay. Now, we did have another case, right? Do you remember the composition when we do f divided by g, the quotient, right? So in that case, we were using this information, and also we were using the information when the g is not equal to 0, right? Because otherwise we'll get division by 0, okay? So that's kind of one more restriction there to us, right? Okay, let me know if you have any questions. Okay, that was question number 4, right? 4. And then we'll do the 5. Okay, everybody seems to be doing good so far. Okay, so let's do the question number 5. Fill the drawings and let's go here. Okay, here we need to find the inverse of this function, right? So f of x is equal to x plus 2 over x plus 5. Let's move the bar over here. Now, do you remember the steps? The steps of the solution, right? How do we do it? Let me put the steps for you so that you can follow them, okay? So, step number 1. Step number 1, replace f of x with y. So that will be the first step. The second step will be switch y and x. The variables, right? Y and x. Now the third step will be solve for y. So it will be some time, taken for it. The fourth step was to check whether the expression we got for y defines a function. Does the expression define a function, right? Now, if the answer yes, then what you will do, you will replace y with f inverse of x, okay? So if yes, if no, say that the f of x has no inverse. F of x has no inverse. Okay, so these are the steps. Try to follow them. I'll give you 5 minutes to work on it as well. And then I will work on it. Can you please put the answer of whatever you got into the chat messages? It will not be a more complicated expression. It will be similarly, approximately the same. It will be also a fraction, right? So can you please put it into the chat messages for me? Okay. Meanwhile, resume the recording and let me put the answer first, right? So where is my pen? Okay, so the inverse function, let me bring my notes closer because those ones I did work on before our class meeting. So the inverse function of f is 2 plus 5x over x minus 1. This is the one, okay? But let's now work on it. How did I get it? First, I'm replacing the f of x with the y. So I put y equals to x plus 2 over x minus 5, right? Then I need to switch the y and the x. So these two x's will be replaced with the y, and this will become x. So this is x equals to y plus 2 over y minus 5. The next step is to solve for y. This, I think, will be like the longest one, right? Because the first two were easy to do. Now, what do we have to do here? We'll have to multiply both sides by y minus 5 to get rid of this denominator. You can also treat it in this fashion. You remember the cross product rule, right? So you can also do it like that. So you will get x times y minus 5 equals to 1 times y plus 2, right? This is another option. Now, we need to open up all the parentheses and move things around. So I'll continue over here. So xy minus 5x equals 2y plus 2. Now, my goal is to solve for y. So I need to concentrate on the y's. First, I need to get them on the same side. Secondly, I need to isolate the y. Therefore, this y is going to hop on the other side. It will change the sign. And this 5x is going to change the sign and hop on the right side, right? Okay, so here we go. xy minus y, because it changes the sign. And then the negative 5x becomes positive 5x plus 2. Now I'll factor out the y because I need to isolate it. I only need one y on the side, right? And what I can do is I can factor it out and then get rid of the factor. So y out, x minus 1 inside equals to 5x plus 2. And then both sides are divided by x minus 1, right? So y is equal to 5x plus 2 over x minus 1. So this is ready for this next step over here, right? Now the question is, does it define a function? And what we need to check over here is that no matter for what value of x I use, I only get one value for y, not 2, not 3, right? So for example, if I use the 1, I'll get it undefined, so not good. If I use the 2, 2 minus 1 is 1, 5 times 2 is 10, 10 plus 2 is 12. So I'm getting only one value, only one possible value for the y, right? And that's because I don't have plus minuses here. If I were to have plus minus, then it means that I will be getting two different values of y for one x, right? So it does define the function. So the answer here will be yes. And if this is the yes, then we will replace this y, as we are told here, with the f inverse. Sorry, I had the f inverse here, right? So we do f inverse of x is equal to 5x plus 2 over x minus 1. So this will be our answer. Okay. Let me know if you have any questions. This was only question number 5. I think we'll be able to do 2 more questions. And then we'll have to stop. Okay, so let's go to the next question. Going to clear all the drawings up and we'll go to the next question. Okay, so here we need to state the end behavior of the polynomial function. And this is a place where you really need your cheat sheet, right? Unless you remember all those cases. We had 4 cases there, right? If anything rings the bell, right? Now, what we were looking at is the leading term, its coefficient and its degree, right? Now, the textbook has it. Our lecture slides have it, right? So what I would suggest is, I'll just give you the answer, but you really need to keep it handy and to be aware of it. So what am I doing here? And I'm not giving you any time here because it's all about looking up those properties. I really doubt that you remember all of them because we didn't use them like throughout the entire class, right? So, it's all about kind of, finding it in the right place. So this is what we are looking for, leading term. Nothing else interesting, leading term. Now be very careful. It might be hidden. So for example, here I could have plus 27x to the power 14. In this case, this would be the leading term, right? Because it's the highest power. It's the highest power. Okay, now this is the leading term. We look at its degree, right? Because it's degree of the polynomial, degree of f of x. It will be 6, right? And the leading coefficient is -1, right? Because of the negative here. So this one is less than 0. This one is even. And this is what we were basing our judgment on, whether the degree of the polynomial even or odd, and what's the leading coefficient? Is it less than 0 or it's greater than 0, right? So these are the two things we were looking at. Now, judging by this, the behavior we should have at the end, of the graph of the polynomial is that it's falling to the left and it's falling to the right, right? So this is what we should be expecting. Falling to the left and falling to the right. Now, there is another way to say it. So another way to say it is as x goes to -infinity, f of x goes to -infinity. And as x goes to +infinity, you don't need this plus, but I just want to stress it out. F of x goes to -infinity still, right? So this was another way of saying it. So you either give the answer in this form or you give the answer in this form, right? But you should be aware of both of them. No more comments. I'm checking my notes if I wanted to mention anything, but I did not. So that, okay. So this is one of those places when we really need access to the cheat sheet. Now, the next one is the next question, but I would like to wait a little bit longer so that if you have any questions, you can ask me. And just keep in mind that you can always memorize them by making a table, like, for yourself, right? This is usually what you do. Like you say here, what's the odd or even, right? And here you can have 0, greater than 0, less than 0. So if you memorize this table and you'll put the arrows here. That's how I used to memorize them, right? So yes, it is possible to memorize them, especially if you review them. Okay. Okay, so let me clear all the drawings and we'll go to the next problem. And I think it will be the last one for today. So this is question number 7. It means that the 3 more questions are left, right? So what I will do here is I will do it in a similar fashion. I'll put the solutions on, I'll scan the piece of paper where I'll put the solution on and I will put it online, but make sure that you review it, okay? Okay, so here, for the polynomial function f of x, we are asked to list all the possible rational zeros. That's another thing we need to remember, that it wasn't the theorem, it was more like a property to us, right? It was coming from a theorem. So first we had a theorem and then we had a conclusion from it. Hey, you know what? Knowing that, we can conclude this, right? So it is coming from the theorem, but it's not what the theorem states. Now, what we do here is we look at the constant term constant term. This is usually the one we marked as the A0. And we look at the leading term coefficient. Leading term, just leading coefficient. It's shorter, leading coefficient, right? So usually it's AN, right? It's the one in the beginning. And this is what I'm matching it with. You remember we had AN x to the power n plus AN minus 1 x to the power n minus 1 plus and so forth, right? A2x squared plus A1x and plus A0. So this is what I'm referring to. We had this general formula of the polynomial function, right? Now what we are looking at there is the AN as the A0. Now over here, if you do the match, let me erase this line over here. If we do the match, then this is the leading term. So the AN is actually the A6, and it's represented by the -3. Now the constant term, oh, you know what? I have a typo here. I shouldn't have the x here. I apologize. There should be no x. Just forget about it, right? Because otherwise, like, you know, I don't have anything there. So now the constant term here will be the one without the x. So it will be this one. Okay? I have to mark my notes that I have a typo and I have to erase that x. Okay. Now, what we were saying is all possible rational zeros could be found from this fraction. So all factors of constant term, right? Term. Okay, over all factors of leading term. That was the formula that we were using, right? And what we did there is we did them with the signs, plus and minus, plus and minus. So think for a moment, how would you list them? What will you do? Because we have the -12 as the constant term, we have the -3 as the leading term. So how would you be listing these values? Think for a moment, like I'll give you a minute to think about it, and then I will list them as well. So I'll put like the equality here and I'll go to the next line. And then we'll discuss it with you. I will be doing this one in pink and this one in green. Okay, so let me start. So I'm listing first all the factors of 12 and putting plus, minus, plus, minus, plus, minus, and so forth, right? So plus, minus 1, plus, minus 2, because 2 is a factor of 12. Now what is it? 3. Plus, minus 3, because it's divisible, plus, minus 4, plus, minus 6, and finally plus, minus 12. So these are all the possible factors of 12, right? And now come all the possible factors of the -3. And thankfully, it's not that many of them. It's plus, minus 1 and plus, minus 3. That's it. Now, the next step for me would be to find all the combinations of this division, of this number by this, of this by that, and so forth, right? So what can I do? I can do 1 divided by 1. I can do 1 divided by -1, right? So from these two types of division, I could get plus, minus 1, right? So that's one of the possible rational zeros that I can get. Now, another one is when I'm dividing positive or -1 by the positive or -3. In this case, I can get a positive 1 over 3, but I can also get a -1, right? And I list it here. So I'm done with the 1. I proceed to the 2. So now I'm here. right? Now, 2 divided by 1 is easy. It's just 2, right? And it could be either positive or negative, depending on the signs. The next comes 2 divided by 3. So I will put 2 divided by 3, and it could be positive and it could be negative, right? Now I'm done with the 2. So I did this, now I'm on to 3. But you see what happens? 3 divided by 3 is a 1, and I already have it listed, right? So since I have it listed, I don't relist it again. So I'm just skipping it. 4. So I can get 4 over 3, right? Plus minus, I can get 4 over 1. I forgot to mention it first, right? Plus minus, and I'm done with the 4. So I listed these two denominators as two possible ones, right? And I'm done with it. Now I'm going on to the 6. So I can divide 6 by 1. I'll get 6, either positive or negative. And I also can divide 6 by 3. But if I divide 6 by 3, it will be 2, and I already listed it. So I'm not going to relist it again, right? And then finally comes 12 divided by 1. So it's plus minus 12. And then 12 divided by 3. Wait, 12 divided by 3 is a 4. So I already have it, right? So I don't need to relist it. And therefore I'm done, right? This is it. So I have 1, 2, 3, 4, 5, 6, 7, 8 multiplied by 2, 16 possible rational zeros, right? And I'm multiplying by 2 because it could be positive or negative, right? That will be it. That will be the answer for this question. Now, if you're doing it in web work, what they might ask you is to put them in order, right? So if they're ordered, they will go from the smallest, and you will put them negative 12, negative 6, negative 4, then negative 2, I think comes, right? Then a negative 4 over 3 or 2 over 3, 4 over 3, right? Then negative 2 over 3. Then what is it? Negative 1 over 3. And then finally the negative 1, right? And then you will be growing to the positive one. So you'll put, oh, you know what? Yes. Oh, no, negative 1 over 3 and negative 2 over 3. They should be over here, right? Because negative 1 is like larger. So here we will start with 1 over 3, 2 over 3, 1, 4 over 3, 2, 4, 6, and 12. So we will list all 18 of them, but we must make them order it, right? So from smallest to largest, right? So this is sometimes when you're asked to do in web work, you might be, right? Something like that. Okay, so let's stop here on this question. If you have any questions, please let me know. And if not, you are absolutely free to leave. I'll have the office hour today from 2 to 3. So if you have any questions, please feel free to come by. I had to cancel it yesterday, right? And if not, then I will see you next Tuesday. This will be our last meeting. So we'll try to discuss all the things apart from the review as well. Okay, have a wonderful weekend and see you sometime. Okay.